Solve the following exercises with the help of the normal model. In exercise 2, the mayor of a city wants to know if the proportion of overweight or obese people in his city is less than nationwide. He knows that nationwide the proportion is 69%. A sample of 150 adults is randomly selected from the city and 97 of them qualify as overweight or obese. We want to test the idea of the mayor at a 0.05 significance level. Again, different authors divide this procedure in 4, 5 or more steps. I summarize it in 3 stages. First stage, set up the hypothesis. Remember, the null hypothesis is the one that can be expressed with an equality. In this case, the proportion in the city equals 0.69. The alternative hypothesis is the one that can be expressed with an inequality. In this case, the proportion in the city is less than 0.69. Notice that what the mayor believes is the alternative hypothesis, not the null hypothesis. This is true in most studies. The main thesis of the study is placed usually in the alternative hypothesis. That's why sometimes it's called the experimental hypothesis. The philosophy behind this, and it is a good philosophy for life, is that if you want to prove that someone is lying, the first step you must make is assuming that they are telling the truth. And you proceed. If you are telling the truth, why did you do this? Why didn't you that? Why did that other thing happen? Until some inconsistencies emerge, if they happen to emerge, and then the individual is discredited. Remember, the idea is, if you want to prove that a person is guilty, the first thing you must do is assuming that the person is innocent. We do that here. To support that the proportion in this city is less than 0.69, we begin by assuming that it is 0.69. And our thesis, or suspicion, as I call it sometimes, is a negation of that. In that case, that the proportion is less. As easy as this stage looks like, it's common that the students don't figure out right what to use as the null and what to use as the alternative hypothesis. And this part is paramount because it cannot be solved with a calculator. There are hypothesis testing calculators that give you directly the p-value and other things, but you need to input manually the right null and alternative hypothesis. Second stage, get the p-value with the appropriate mathematical model. As I mentioned, when working with the parameter proportion in a population, you are expected to use the normal model. Most hypothesis testing calculators or softwares are programmed to use the normal model for proportions. We check that the sample is random, contains more than 10 successes and more than 10 failures, and is very small compared to the population, so the normal model applies. This normal model is going to be applied on the basis of the null hypothesis. We saw in the previous chapter that if the proportion in the population is 0.69, the sampling distribution of sample proportions will follow a normal model with a mean of 0.69 and a standard error given by this formula. This is approximately 0.038. The most common mistake in this moment is using here the proportion in the sample instead of the proportion in the null hypothesis. And I understand this mistake because that is done when building a confidence interval. There are 2 main reasons why it would be a very bad mistake to use here the sample proportion. First reason, we use the sample proportion as an approximation of the population proportion when the latter is unknown. Since here we work as if we knew the proportion in the population, we assume that it is 0.69, there is no value in using an approximation. The second reason, and most important, is that in order to test this hypothesis, we have to use it. We must use it and see what inconsistencies emerge, if any. We use it here and here to build our mathematical model. If you don't use it here and here, where else do you plan on using it? There is nowhere else. These two objections don't apply to the building of a confidence interval because in a confidence interval we don't assume that we know the parameter in the population, and also we don't have a hypothesis that we want to test. Here we do. That's why I color-coded this in green. This particular mathematical model is a direct consequence of the null hypothesis, so it is hypothetical itself. Sometimes I say it with a play on words. If this hypothesis is false, all this mathematical model falls. On the other hand, we have something that is not hypothetical at all, something that is a matter of fact. This something is the sample. I write here in red the proportion observed in our sample. This sample suggests that the proportion in the population could be less than 0.69, but how strong is this suggestion? In other words, how compatible is this observation with our null hypothesis, which is represented in this mathematical model? We answer these questions with the help of the p-value, which is this conditional probability. It is the connection between the null hypothesis and our data. What's the probability of selecting a random sample with a proportion as small as 0.647 or even smaller if it is true that the proportion in the whole population is 0.69? A normal calculator will tell you that this is 0.129. This is bad news for the mayor. The mayor was probably very happy with the sample from his city that had less proportion of overweight or obese people than the whole country. But a statistician will tell him, this sample, whose proportion is 0.647, is perfectly compatible with a population whose proportion is 0.69. Therefore, the proportion in your city could very well be 0.69 or even more. The difference of 0.043, that's to say 4.3 percentage points, observed in the sample is not statistically significant because the p-value is so big, much bigger than 0.05. In this third stage, you write a sentence that expresses the conclusion in plain English. This sentence shall provide the p-value because it is not the same failing to reject the null hypothesis with a p-value of 0.06 than with a p-value of 0.13. Some authors recommend to get the C-score of the proportion in the sample, which is commonly called C-stat or C-test. As soon as we see a C-stat of a bit less than -1, we know that this sample is perfectly compatible with the null hypothesis. If the C-stat was close to -2 or beyond -2, we would be getting another conclusion. In exercise 3, we see two new things. The null hypothesis, as we said, is an equality, but in this case we are not comparing a proportion to a number, but a proportion to another proportion. A company claims that its medicine is as effective among men as it is among women, so we work with the proportion among men and the proportion among women. In this exercise, we are not asked to test if among men it is less or if it is more. We just want to test if it is equal. In other words, the negation, the alternative hypothesis, is simply different than. This is called a dual-tailed or two-tailed test, as opposed to a single-tailed or one-tailed test like in the exercises we saw before. But in order to do our math, we have to compare to a number, so we expressed the hypothesis in this other way. Now we use the same mathematical model as in the previous chapter. We are under normal conditions, the samples have room for more than 10 successes and more than 10 failures, they are randomly selected, and they are reasonably small. We know that the sampling distribution of the difference between two sample proportions will follow this mathematical model. According to our null hypothesis, this difference in the population is 0. One sample size is 200 and the other is 100. And here we have a situation. In the previous hypothesis test, we were comparing a proportion to a number, so we put that number here. Since in this test we compare a proportion to another proportion, we don't assume anything about the value of any of them. In other words, we don't have a hypothesis to put here. All we know is that these two values must be the same. In a case like this, it is valid and it is necessary to use an approximation from the sample. This approximation is commonly called the pooled proportion. The idea is this: since according to our null hypothesis, the gender doesn't make any difference, what we do is forget about the gender. We combine both samples, men and women, in a single one, and in this big sample we have 300 individuals among whom, after taking the drug, 38 plus 102 got the cold. This gives a total proportion of 0.467. In simple terms, the pooled proportion is the proportion in the combined sample. And this is what we use as an approximation of the proportion among men and the proportion among women. Remember that these two are supposed to be the same per our null hypothesis. In this way, our final mathematical model here is a normal distribution with a mean of 0 and a standard error of 0.061. This is how the difference between two sample proportions, one of men and the other of women, should behave according to our null hypothesis. The matter of fact is that when we picked a sample of men and a sample of women, the difference in their proportions was not 0. It was 0.13. It seems to me that this is very inconsistent with our null hypothesis. What's the probability of observing a difference of 0.13 or more than 0.13 if it is true that the difference in the population is 0? Using this normal model and a calculator, you will get 0.017. Now we must multiply this by 2 because we are in a double-tailed test. Let me explain this. Here in the middle we have our hypothesized value, and in this extreme we have the observed value. The probability 0.017 is the probability of being here. This is the only way of being as big as or even bigger than our observation. But now we don't test for bigger, we are testing for different. There is another way of being as different as or even more different than our observation. This other way is here, so you must multiply this probability by 2. Finally, the p-value is 0.034. This is less than the common level of significance, so this study provides strong evidence that the developer's claim is not right. The evidence strongly suggests that the effectiveness of the drug is different among men than among women. P-value 0.034. A limitation of this test is that it tells us that the effectiveness among men is very likely to be different from the effectiveness among women, but it does not tell us in which gender the effectiveness is greater or how much greater. We can answer those questions with a confidence interval. Question B. Complement your conclusions with the help of a 95% confidence interval. Of course, we want the confidence interval of the difference between the proportion among men and the proportion among women. We saw in the previous chapter that the standard error of the difference between sample proportions approximately equals this expression. Here we must use the proportion in the sample, the proportion for men and the proportion for women. Here we don't use the pooled proportion because we are not assuming that both proportions are the same. The standard error is approximately 0.060. For 95% confidence, we need a margin of error of 2 standard errors. That's to say 0.12. This is added to and subtracted from the difference observed in the sample to get the confidence interval. This confidence interval is entirely positive. It does not capture the zero. As we explained in the previous chapter, this means that the minuend, in this case the proportion of men, must be greater than the subtrahend, the proportion of women. We can even say how many percentage points the proportion of men is greater than the proportion of women. This is consistent with and more informative than the result of the hypothesis test. Keep in mind that these are the proportions of individuals who got the cold after taking the drug. The fact that the proportion is greater among men means that the drug is more effective among women. Here the nice sentence. We are 95% confident that the drug is more effective among women than among men. In particular, we are 95% confident that after taking the drug, the proportion of individuals who still get the cold is between 1 and 25 percentage points larger among men than among women.